Hi, this is Mr. Merrill, and I just wanted to do one of these quantitative energy conservation problems for you. So, even though this is a energy conservation problem, we have a hammer slides down the roof of a house and lands on the ground below. Even though we're going to treat it like an energy conservation problem, we're going to start out by thinking about the forces that are acting on the hammer at all points in times, just to be thorough. So I have two force diagrams, one representing when it's sliding down and then one representing when it's in free fall to the ground below when it's doing that little trajectory there. So why am I doing this? Well, I want to point out, look at this, we have a gravitational force that is conservative, a normal force that is non-conservative, a frictional force that is non-conservative, and a gravitational force, the same gravitational force that's conservative. Now why am I doing that? Because next I have to think about a system. What do I want to include? Now, I'm going to include the hammer, obviously, but I'm also including the Earth. Because if I recognize this as a conservative force, then I can assign a potential energy to what it does, and I don't have to think about work. But for these non-conservative forces, I can't assign any potential energies to them. I can't think about them quantitatively. I can't assign a number to their energy. But I can assign a number to their energy transfer by thinking about them adding or removing energy from a system. What I'm basically saying is these non-conservative forces we should think about as whether they do work or not. So here we can begin to go to our energy diagram. Again, inside of the system I'm going to include the hammer and the Earth, and think about the process that's happening here, the event. So with every kind of energy problem, we're interested in a before and after picture. This isn't two hammers, this is the hammer at some earlier time and the hammer at some later time. That's the initial and final business here. So in the beginning it starts at rest, so we're not going to have any kinetic energy, but we are, because I've defined h equals 0 to be down here, going to have some gravitational potential on. Now, like I said, the roof itself is not part of the system. But that roof is going to be doing something. It's going to be exerting a external force, because it's not part of the system, external frictional force in the opposite direction of motion. Basically the hammer is going down the rooftop and the kinetic friction is in the opposite direction. What does that mean? That means that the frictional force is going to be removing energy. I mean, that's what friction does. It makes things go less fast. It makes things not reach as high in the air. It reduces the energy in the system. It doesn't add energy. So let me make my notation here a little better. So we would say the work done by the non-conservative force of kinetic friction, that's what this little block of energy removed represents. And what's happening once it finally reaches the ground? Well, there is no gravitational potential energy, and so all its energy must be stored as kinetic, or energy of motion. So now we can think about what the law of energy conservation tells us. It tells us that the initial energy plus any additions or removal of energy equals the final energy. In terms of what we have here, the gravitational potential energy, in addition to any work added or removed by this frictional force, equals the final energy stored in kinetic form. So what we need to do is we have things to describe the gravitational potential energy, and we have things to describe the kinetic energy, but we need to calculate the work. And that's usually the biggest pain in the butt, but it's not too bad. So here we start out with that same force diagram, and I've gone ahead and calculated the components for these forces. Again, if this is the incline angle, then this angle between the negative y-axis and the gravity vector is also that same angle. So you can see this, you've done this a million times before. So why did I do that? Well, because I know that work, energy added or removed, is equal to the magnitude of the parallel component multiplied by the distance that force was applied over. So here the normal force is not going to be doing any work because it's perpendicular to the direction of velocity. It doesn't have a parallel component. And the gravitational force is not going to do any work because I said it's internal. It's part of the system. I've taken care of this basically by assigning a gravitational potential energy. But I do have to concern myself with this frictional force. First of all, it's negative because it's in the opposite direction of motion, and it doesn't have two components. It's entirely in the opposite direction of the velocity parallel to it. So we have a model for kinetic friction. We say that's equal to the coefficient times the normal force. And what I'm doing now is just solving for the normal force. I think most of you can just visually see the normal force is equal to this component. And substituting that back into the previous line, we get this solution for the energy removed by friction. So carrying that along, going back to the same equation that we got from our energy diagram, we can now plug in all our relationships, mgh for gravitational potential energy, plus what we just calculated for the work done by friction, and 1/2 mv squared for the kinetic energy. Let's pause. Maybe you didn't notice, but this is probably going to cause some confusion for some of you, because h is not 5, even though my diagram was mean and labeled it like 5. H is the distance above h equals 0, which is this distance here. So this is what I actually want to include in whatever I'm calculating. Well, you can see that it's obviously 5 meters plus some. That plus some is this distance here. Well, you can find that distance there with a little bit of trig. If this is 37 degrees and this distance here is 5 meters, then the sine of 37 degrees must equal that opposite side. I don't know what I'll call it L. So L over 5 meters. So L must equal sine 37 times 5. And this is a 3, 4, 5 triangle, so that's 3 meters. And with a little bit of rounding, this is not the exact angle. So what is the actual distance? This actual distance is not 5, it's not 3, it's 8. It's the total distance off the ground. This being 3, this being 5. So doing some rearranging, we see that every term contains a factor of mass, so those cancel out. Then we can rearrange to solve for the speed, so I'll let you check the algebra there. And then plugging in numbers, you should double check me, but I got 11.2 meters per second. So that's saying when the hammer impacts at the ground, it will impact with the speed of 11.2 meters per second. Now this is actually a problem that can be done without using the idea of energy conservation at all. You could calculate the acceleration down the ramp, calculate the components of the velocity when it leaves the roof, solve a projectile motion, define the components when it impacts at the ground, use Pythagorean theorem to find the speed, but it's a very complicated problem to do that. So hopefully you see the power of invoking energy conservation. Though this I wouldn't call an easy problem, it's certainly much easier than the other choice of doing all those things that I mentioned. So I think when you're doing these problems, just be careful with solving for the work done by friction. More importantly, thinking about what the normal force should be. So usually that involves making a force diagram and relying on things you've already learned about, how forces balance and all that good stuff. Alright, so hopefully that cleared up a few things.